Okay, we're given the function f of x equals x to the fourth plus 4x cubed minus 18x squared minus 9. We are asked to find the critical values of this function. We need to determine the intervals over which it is increasing and decreasing. We need to determine the maximum and minimum values, or another way of saying that is to classify the critical values as maximum or minimum points, relative max or minimum. We need to determine the intervals over which the function is concave up or concave down. We need to determine the inflection points of the function. We need to sketch a graph of the function, and we need to verify. In my case, I'll be using a graphing calculator to do that. For the purposes of speed and efficiency, I did all the algebra and I drew the graph beforehand. I just can't do a video in a reasonable amount of time while working through the algebra and narrating and talking at the same time. So I'm just going to explain kind of what I did and how I got there and all that. So in order to find the critical values of the function, we need to take the first derivative. And after doing so, we get, let me zoom in a little bit. We get 4x cubed plus 12x squared minus 36x. I expanded that and set it equal to 0 to get our critical values, one of which will be from this first term. 4x, I set that equal to 0, and you get x equals 0 out of that. The second term I plugged into the quadratic formula, and from that I got two x values. I got negative 3/2 minus 3 times root 5 over 2. With a decimal approximation of that is negative 4.8541. The other x value of our second term is negative 3/2 plus 3 times root 5 over 2. And the decimal approximation of that is 1.8541. I plotted those values on our number line down here. And then I picked values lesser and greater than those critical values in order to determine the, where it's increasing and decreasing. So when I put those, for those values, I picked negative 5, negative 1, 1, and 5, and I took each of those values and I put it into the expanded first derivative, and after doing that I got these results. As you can see, putting negative 5 in there, you get a negative value, therefore it will be decreasing. A negative 1 in there, you get a positive value, therefore it's increasing. If you put a 1 in there, you get a negative value, therefore it is decreasing. And putting a 5 in there, you get a positive value, therefore it is increasing. So from this graph, you can basically see where your minimum and maximum values are. But to verify that, we take our critical values and we put them into the second derivative. So I went ahead and got the second derivative, which comes out to be 2x squared plus 24x minus 36. Then I went ahead and expanded that and set it equal to 0. Expanding it and setting it equals 0 is also how you get the inflection points, but I'll get to that in a sec. So anyway, I expanded it and I put my critical values into the expanded second derivative, and this is to verify whether those are maximum or minimums. So putting negative 4.8541 into it, we get a positive value. Therefore, it is concave up, which verifies that it is a relative minimum. Putting 0 in, we get a negative value. Therefore, it's concave down, and it is a maximum. Putting 1.8541 in, we get a positive value. Therefore, it is concave up, and that will be a minimum. And then to get our inflection points, we expanded our we expanded our second derivative, and we determine our x values, and expanding it, we get the terms x plus 3 and x minus 1. Setting each of those equal to 0, we get x equals negative 3 and x equals 1. And I actually did that on a different sheet of paper, but you can kind of see what putting those values on a number line as well, and then selecting values greater and equal to each of those. Basically the same thing you do with the first derivative to find whether it's increasing or decreasing. But anyway, you can see that the concavity of the sign changes at these values when you pick values greater and lesser and put it into the expanded second derivative, as I've done here. You can see that the sign changes. It's going from positive to a negative at negative 3. It stays negative all the way till 1, where it then becomes positive. So these 2 points, negative 3 and 1, of your second derivative are your inflection points. On the graph, I indicated that with basically I indicated the concavity in green, and I've indicated where the inflection points are. So let's talk about our graph real quick. These are the values I plugged in the calculator, and I did that to get these. I should zoom in on that a little bit. Once you plug that into the calculator, here's your, in blue is your original function. This is your first derivative, second derivative. Okay, so as you can see, at our value of negative 4.8541, we drew that way down here. And when plugging that in, our y value is going to be way down here, which is negative 335.4. That is a minimum value right here. You can see that on our graph. At 0, you can see we have a maximum value, and at 1.8541, you can see we have a minimum value. What else did I want to say about this graph? Our points of inflection, I circled, and I used different colors. I started and stopped with different colors at the points of inflection to indicate the concavity and where it changes signs. So I don't know if you can see this real great, but from negative infinity, from negative infinity to negative 3, we can see it's concave up. It changes signs at x equals negative 3 and is concave down until x equals 1, and then, as I indicated in green, it is now concave up again, and those are our points of inflection, which we found here. Negative 3, and x equals negative 3, and x equals 1. So x equals negative 3, we have a point of inflection, and x equals 1. Oh, sorry. We have a point of inflection right there. And the y values for that, you can see, are 1, negative 22, and negative 3, negative 198. And these are all verified in our calculator. Interestingly enough, you can see that where our zeros are for the second derivative is where our points of inflection are. It's interesting to be able to see it on a graphing calculator. So verifying this on the calculator, obviously I moved these over to here, but graphically, darn it, that kind of blurs that out. Graphically, I put our original function and first and second derivative into our calculator, and I went to our table and I put our x values in there to test the different x values. That's how I could get our y values for a lot of this. And then, where am I at? Okay, to graph that, basically, I get this, and the one in blue is, in fact, our original function. As you can see, it looks very similar to the graph that I have here. Why is that blurry? There we go. I think that's all I'm going to do. I'm sure I'm forgetting stuff to talk about, but that's it. I'm at about 13 minutes, so okay.